Welcome back to Dunwoody Heat Transfer. This is problem 724 from Bergman. Sorry, the first video I did for this did not have sound, so I'm giving it a second shot here. I thought about trying to voice over the past one, but that probably got a little too messy. So we've got a situation here where we've got some hot plates coming out of a furnace. They're being cooled by some ambient air flowing across them, and we're told that this conveyor speed is lower than the airspeed by a significant amount. So our known values, air temp and velocity, plate dimensions, and we know the initial temperature of these plates. So we read the problem statement. We're looking for two things. We're looking for the initial heat transfer rate, and we're looking for the rate of change of the plate temperature. So looking at the system here, we know a number of things. Oh, we also know, we know this is 6 millimeters. We know these are 1 meter on each side. We know these values here. U infinity is 10 meters per second, and T infinity is 20 degrees C, and this initial temperature is 300 degrees C. Yes. So as we look at that, what are some of the assumptions that we might need to make for this guy? So one, we're going to assume no radiation, or negligible radiation. 2, conveyor does not impact heat transfer or convection. And 3, plates are isothermal. It's a good assumption at first. What's going to happen as time goes on? Well, the temperature at this leading edge is going to get colder than the back edge because our air is warming up as it passes along the length. So this is not necessarily good at the end, but initially, okay assumption. Fourth, we're going to assume that we have constant properties. No heat transfer from sides. So these edges are small. So this little bit here is not going to give us much heat transfer. And if we looked at the area, that would be a pretty small percentage, even if we did include that bit. So we're only looking at these giant 1 meter squared and the corresponding piece on the back side of this guy. Those areas, not the edges, not the 1 millimeter, 6 millimeter by 1 meter times 4 edges on each of these plates. And then last, we got constant properties. We're going to say critical Reynolds number equals 500,000. So that's our transition to away from laminar. Alright, so with that, now we need to do some properties. So for the steel, T is 300 degrees C, or what is that, 573 Kelvin. From table A1, 1010. AISI 1010, 1010. We have K. When we do that interpolation, we get 49.2 watt per meter Kelvin. C, specific heat, is 549.9 joules per kilogram Kelvin. And last, for the steel rho, is 7832 kilograms per meter cubed. For air, we're going to look at that film temperature. It's going to be Ts plus T infinity over 2. So we get 573 plus, for that bit, plus, 20 plus, what is it going to be, 293 over 2. So our film temperature for that is 433 Kelvin. This is from table A4 at 1 atmosphere. And the things we want there are nu, K, and Prandtl number. So when we look at that, we get for nu 30.4 times 10 to the negative 6 meters squared per second. K is pretty low. We get 0.0361 watts per meter Kelvin, and our Prandtl number is 0.688, and there's no units in that guy. So we've got our properties, and now what do we need? So what we're looking for here is our initial heat rate, right? So it's going to be Q h bar A delta T, essentially, Newton's law of cooling. So what are we looking for with that? We know delta T, we know A. We're really looking for this h bar. So we need to find some correlation that gets us our heat transfer rate. Oh, no bar on the Q there. H bar A delta T. And so we're going to look for a Nusselt number average over the area. Now if we look in the book, we'll need to find a Reynolds number. So let's find the Reynolds number first. Let me back up a little bit. Reynolds number. So we're going to have U D, oh not D, L over nu. So we get, what is it, 10 meters per second times 1 meter over 30.4 times 10 to the negative 6 meters squared per second. So our meters squared are going to cancel out, our seconds are going to cancel out, perfect. And when we plug that in my calculator, what do I find for my value here? So hold on a second, just running a little. Alright, I'm back. So we plug that in the calculator. We find that my Reynolds number is 329,000, give or take. So what does that mean? Laminar flow. So we need to find a correlation where we get laminar flow. We need an average heat transfer coefficient, and it's over a plate. So we look in the book for that bit. We find this correlation, Nusselt number, average, is 0.664 Reynolds to the 1/2 Prandtl to the 1/3. Filling in numbers, 0.664, 329,000, 1/2, 0.688 to the 1/3. Find my average Nusselt number is 336, and that again is going to equal h bar k, h bar L over k. So h bar 336 times k over 1 meter. Excuse me, that shouldn't be over that. It should be HL, 1 meter, over K. So K is, oh no, sorry, H is, yes, times K. There we go. I had it backwards. I was right the first time. 1 meter. K is 0.0361. So then I plot those together. 336 times 0.0361. I get 12.13 watts per meter squared. Kelvin is H bar. So then Q is that 12.13 2 meters squared. So we have two sides for A, and our delta T is 280. So our initial heat transfer rate is 6792 or 93 watts. I think the book found 6780, pretty similar. So that was that first bit. And then the second bit, the heat rate at the rate of temperature change. So what do we need there? Where does that come into play? Well, we have from our energy balance, we'll have what we have is storage. Change in that temperature. It's going to be what we have leaving, right? So negative E out. So we have rho C V dt equals negative Q, right? So that first bit that we had there. So now we need these properties from our materials for the steel. V for the steel is going to be 1 meter by 1 meter by 0.006. Rho was, what was that, 7832. And C was, what, 539? 549. Equals negative 6793. So dt is 6793 over 7832, 549, 0.006 dt then is negative 0.263 degrees Celsius per second. So right initially we're losing about 1/4 of a degree C per second due to this cooling. So not super fast, kind of what you'd expect for airflow over a plate. 10 meters per second is moving a little bit. It's not super fast, but there's a lot of thermal energy stored in that large plate. So I hope this was a helpful video for you. And I again apologize for not having sound on the first one. I probably won't get the other one uploaded tonight, but we'll get that squared away, 785, shortly. Thank you for watching.